So now in physics, sines and cosines come up a lot. We study the physics of oscillations, masses on springs, traveling waves, all kinds of things. And so it's very helpful to know the derivatives of sine and cosine. So I'm simply going to state these. The proof of the derivative of sine is maybe one of my favorites. And yes, I'm aware that's very nerdy to have favorite calculus proofs, but so will you once you see it. But in any case, if I define a function f of x as sine of x, then f prime of x turns out to be cosine of x. Okay. Now, I've been writing this in Newton's notation, which is f and f prime, and I'm going to stick to that for now, but I'm going to mix up the notation once we do some practice problems. So this is the derivative of sine. If instead I want to know the derivative of cosine, so f of x is equal to cosine of x. You might guess, well, maybe if sine derivative is cosine, then cosine's derivative is sine, and you'd be very close. You can actually figure it out by looking at the graph and thinking about slopes. You can make a pretty good educated guess, and you can in fact figure out that the derivative of cosine is negative sine of x. So, like I said, it's killing me a little bit to not show you anything about the proofs of these, but I'm trying to keep it short and efficient for your sake. However, if you look at the graph of sine of x and you look at the graph of cosine of x and you think about the slopes of those graphs, you should be able to convince yourself conceptually that these functions look about right. So just as I said I was going to show a little bit more of Leibniz notation, on this next slide I'm going to show you how I would write these with Leibniz notation. So there you can see from an earlier slide, you could write this as f of x equals sine x, and then df divided by dx, which is often said df dx, even though there's a fraction bar there. Df dx equals cos x.